All right, so I guess, yeah, we're started here. My name is Billy Korando. I'm a developer advocate with IBM. We have a lot to get through in this kind of pared this down from a much longer workshop. So I'm just going to go ahead and get right into it. This is Spring on Kubernetes 101. So Kubernetes has seen a huge amount of growth and popularity since it was released back in 2014. And so what's kind of contributing to this growth and popularity is it's very flexible. As long as what you're running is in a container, then Kubernetes should be able to run it. It shouldn't have any issue doing that. Also, Kubernetes is very extendable. So Kubernetes is kind of like a base, and on top of that, you can kind of extend a lot of capabilities to it. So you have service meshes like Istio, you have pipeline tools like Tecton, you have package managers like Helm, and then you even have something like a more PaaS-like offering like OpenShift that can all kind of be built on top of the Kubernetes architecture. Oh yeah, also want to mention one thing. If you have any questions at any point during this presentation, be sure to put them into the comments, and I am trying to check them regularly. Like I said, we're pretty tight on time, so I may not always be able to get the questions, or I may, if I'm going to be answering later on, I just may not really respond until I get to it here in a few moments or something. But if you do have questions, go ahead and post them in there and try to answer them as we can. But for the last part is that, while Kubernetes is very flexible and very extendable, it does have a very, very steep learning curve to it. I definitely felt that as I tried to start learning about Kubernetes over about the past 2 or so years. So hopefully we're going to make that a little bit smoother with this presentation, get some of the underlying concepts in there to make it a little bit easier to understand. So this presentation, it's Spring on Kubernetes 101. So I'm specifically designing it around, like myself, I'm a Spring developer. I'm a developer first more than an operations person. So I'm designing it around what are the things developers need to know and understand to be able to be effective with Kubernetes. And also when maybe running a local cluster for Kubernetes, or maybe a development cluster, kind of some of the things you would need to know for like debugging, maybe editing a Kubernetes cluster or something like that, as you're kind of working through and developing an application. It's not really based upon trying to administer a cluster that's running at a massive scale in production. That's not the goal of this presentation. So what are the learning objectives? We're going to look at Kubernetes architecture, kubectl, kubecontrol, whatever you want to call it. This is the Kubernetes command line interface, though. Then also some of the design considerations for applications in Kubernetes. And then finally, how to configure applications in Kubernetes as well. So Kubernetes architecture. So as often is the case in computer science, what seems like a really new and interesting concept actually has its basis often back in the 1980s. And that's actually no different than with containers. Containers have recently seen a huge surge in popularity, but really they actually kind of initially started from concepts developed back in the 80s, and just kind of seen a recent surge in popularity because of Docker, which we'll touch on here in a few moments. But why are containers so advantageous? Why aren't they, is it just something beyond just the hype? So they have several key advantages. One, they encapsulate all of our run dependencies into a single package, which then makes it much more portable. You no longer need to install all the software an application needs to run, which, could be the Java runtime, could be an application server, could be a bunch of these different underlying dependencies. All you need is the containerization software to be able to run that application. They're also very shareable. So you can easily share images between different computers, within your organization, even outside of your organization. And finally, they're much more lightweight when compared to a VM. And that's because, unlike with a VM, when you're having to have an entire guest operating system, a container can make use of native operating system functions. So it's just a lot more lightweight when compared to a virtual machine. So of course, when we're often talking about containers, what we're really talking about is Docker. And again, that's kind of what caused the surge in popularity with containers over the recent years, is when Docker went generally available back in 2013. and it's effectively the de facto choice of containerization. There are others out there, but probably at least 90% of the market is based on Docker when it comes to containerization. So that's primarily how we're going to talk about containerization when it refers to Kubernetes in this presentation. So to be able to build a Docker image, you have to create a Docker file. And so the base concept within a Docker file is you can provide a from, and that's where the base image you're going to be building from. In this case, I'm using the adopt OpenJK image, specifically the hotspot JRE11 tag of it. And then here, you would copy in whatever sort of logic, the actual stuff that's going to be running for that Kubernetes container, or for that Docker container. You could be copying that in. In this case, it's just an extremely simple hello world class. And then finally, either with a command, run, or entry point, you're going to give some sort of command that's going to be executed when this container starts up. In this case, then just Java and then the hello world class that I passed in. So we have the containers, and then to build it, we do Docker build. The period refers to the current folder that we're in. And then the tag is that us.icr.io. That is, in this case, a private container repository in IBM Cloud. But that would be like the first part of the tag, just where the container repository is going to be. Then a namespace. And then finally, the image name or the repository name where the image is going to be stored. And then last is the specific tag to it. So it kind of works somewhat similarly to the Maven namespacing that you kind of see, where you have like a group ID, a version ID, and then a specific tag number, and then maybe also the repository as well, where you would define that within your Maven file. This kind of works overall pretty similarly in trying to provide those kinds of coordinates to it. So if we build that, in this case, it's going to be 3 different steps. It's building based upon that previous hotspot image, and then it's copying in the file, and then the command to run, and then when we run it, it just again prints out hello world because it's not really doing a whole lot. So a few terms I went over just to kind of touch on them and maybe how to better understand them is image, and you can kind of think of that like a class. So in that Docker file, the from, the copy, the command, that's kind of defining like all these like, maybe method names, field names, and stuff like that within this Docker image, kind of like how you would within a Java class. So then you also have a container, and that's like an instance of a class. And just like how a class can have many instances within a JVM, you can have many instances of a specific image. And then, of course, as you run those images, or as you have different instances, like in a Java class, they don't necessarily have to be the exact same as one another, but they're going to have the same underlying traits. So maybe as a container runs, you may save certain state to it or something like that. It could kind of change it over time, but it's still going to have that same underlying concept that's being built from. And then finally, you have also layers. And this is an important concept within containers to help save time and space by caching previous layers that have already been built. So what does that look like? Well, we have the container image I just built, and it's just under 240 megabytes. Now, if we actually look and break it down what's in there, we can see it's made up of many different layers. And at those very 2 top layers, the copy and the commands that I did in that Docker image files, those are different layers within the Docker image. Those are the 2 I added, whereas the from and then all the layers that it's built off of are kind of from before. But if I was to push it, assuming that the that from command, the .openjdk JRE11 hotspot is already cached either locally or in my container repository, then that's all. The only things I had to push are the only 2 layers, like the hello world class and the command I'm running. That's the only thing I actually had to push up. So that can actually save you a lot of time and bandwidth when doing that. Instead of having to push up the whole 240 meg nearly, I only have to push up the just like the 500 bytes of space from just the class I created. Of course, it's not going to really be like that for like a real application, but it does kind of show you how that can actually save a lot of time and bandwidth. Container registries, they work pretty similarly to how Git works. So developers or whoever, they push a container or push an image to a container repository. And then on the other end, you could pull images out of a container repository or container registry. And that's actually how Kubernetes works. When you're having an application run on Kubernetes, you're not like how you would probably within like a application server like WebSphere, WebLogic, or something like that. You're not actually yourself pushing the container or the application to it. You're just telling Kubernetes where to pull that image from. And again, that's something they're going to get to here in a few moments. So for container registries, Docker Hub is a really popular one for having a public registry. But for all of your cloud platforms, they all have their own private repositories as well on them. So you can have, so if you're running your own proprietary code, you can kind of keep that in a secure location that other people can't get to, because you're generally not going to want to have for your organization the proprietary code for running your business logic out there in a public location. So container orchestration. So, I can run a few containers on my local system, or I can, if I wanted to, administer running a few containers out on the server somewhere. But once you get beyond a few containers, it becomes impractical for an individual to actually kind of run and make sure that they're scaling up containers to meet demand, tearing down containers if they run into issues. You're not going to be able to handle that beyond a few containers at a time. Once you get to dozens and let alone hundreds of thousands, like many organizations would be running, you would need dedicated software for actually handling that. Hold on one moment. Need getting pinged on Slack. Oops. Oh, all right. Sorry about that. All right. So you need a container orchestration software to handle that. And that's exactly what Kubernetes is. All it is doing is you tell it how many containers to be running out there, and it tries to meet that demand for how many containers you want to have operating. And then from that, Kubernetes just has an external API that you can then add additional capabilities into, kind of like I mentioned earlier, with like service meshes, pipelines, package managers, or even like a more PaaS offering. So that's, again, at a core level, all Kubernetes is doing is the same. How many containers you have running, when you should add more, when you should take them away, and stuff like that. So a few months ago, I was listening to an interview with Kelsey Hightower, who's very important and popular, a developer advocate with Google, who kind of does a lot in Kubernetes along with all cloud things. And he gave a really good quote here and I just want to kind of repeat it, where he's like, if you understand the Kubernetes API, that's the most important piece of that ecosystem to understand. And you kind of, from there, understand more about the overall Kubernetes ecosystem. And I've kind of really come to appreciate that as I've gotten more familiar with Kubernetes. Once you understand like how the API works, you can understand a lot more about it itself. So let's start looking at the Kubernetes API. Here is an example of a YAML file defining a deployment, so an application out there in Kubernetes. At the top is the API version, and if you provide this, so there's like some backwards compatibility or forwards compatibility as well. So that way, if you want to update to a newer version, there's going to be like maybe like say apps v2, you can have some time to transition over that. It's not like a hard cut over to that, because you can define the API version within the file that actually pushing up. Then you can define the Kubernetes resource type, in this case, a deployment, some metadata for identifying that Kubernetes resource out on the cluster, and then the specification that's going to be unique to that Kubernetes resource. So here in this example, I'm having how many instances of this container do I want running in my cluster, in this case 2, and then what is the image I'm going to actually be executing, where I'm going to be pulling it from. Here I'm referencing an image that I have out on my Docker Hub. So API version, kind, metadata, and spec, these are all going to be fields common across all Kubernetes objects when you're defining them in YAML or JSON. They're all going to have these fields, but from there, like under spec, that's going to be specific to each kind of Kubernetes resource you're defining. That's always going to be very different. So Kubernetes has this concept called a control loop, and it kind of works like a thermometer within like your building or your house, where it's just like, okay, I want it to be at 72 degrees And so if it's colder than that, then the thermostat will kick on the heater to warm it up. If it gets warmer than that, then it will kick on the AC to cool it down. It's always going to try to get to that point where you set it to be. And that's kind of what Kubernetes also does here. Let's see what that looks like. So like I said, I set it to 2 replicas. And so I see I have 2 instances of my container running. Now, if I tell Kubernetes to delete one of those instances, that's deleted. Now, if I go back and get the pods that I have running, and we'll see it here in a second, well, I get back 2 pods, and you can see how that second pod, or in that second callback, one of the pods has 6 seconds for how long it's been around for. And so that's what it's going on here, is that because I said I want 2 instances of this running, if at any point it's less than 2 instances, Kubernetes is going to try to then start up a new instance. If I was to try to add another instance somehow, then Kubernetes will kill it because that's, again, more than 2. So you declare the desired state you want Kubernetes to have it running, and Kubernetes will continually try to run or work to maintain that current state. So yeah, as I mentioned, there's 2 replicas, and that's the desired state Kubernetes will always try to maintain. So let's talk about networking. So if I was to go to Kubernetes pod wide to kind of get like maybe the IP address because I wanted to access the service I have out there, I see these IP addresses 172.30 and 10.144. So I try to curl those and call 8080 because that's the default port Spring runs on. Well, I get these operations timed out. Okay, so if I go to nodes because, okay, yeah, I heard Kubernetes runs on nodes, and so maybe that's what I need to do. So I get nodes, and okay, external IP, okay, that's starting to make sense. Okay, if I use that, that should work. But of course, that also doesn't work. I still get an operation timed out. So my pods, they're running inside a node, and they get their own IP addresses. That's part of the internal network. And so when I try to hit that, well, it's going to fail because that's an internal network, and those are going to be rejected because I'm on the external network to it. So let's talk about some of the other common Kubernetes resources. For example, a service like node port. I can define a node port, and you can see here in the spec, I have a selector, and it has app hello services. Now, if you think back to deployment YAML, which I showed earlier and I have down here, I also gave it in the metadata a label of app hello service. So that's how this connection is being made. When I'm telling the service node port I'm creating, the way I'm telling it to reference these other pods out there is through that selector and that label in the metadata. So now if I push this service out there, push the service out there, it has this port address. And so this node port, it provides a tunnel from the external network to the internal network of this Kubernetes cluster. So now, if I took that external IP address when I looked up the Kubernetes node, so like I see back here, you can see at the bottom, the 169, that's the external node for this Kubernetes cluster. I can now actually connect to my hello service. I can get the hello world back when I call 169 and use the IP or the port number for the node port I created. That's how I can communicate into my Kubernetes cluster from the outside. So just to kind of review the common Kubernetes resources: deployment, pod, service, replica set, volume, ConfigMap, secret. There's many more than this, but these are the ones you're going to probably be most often working with. So let's get into kubectl, the command line interface, so you can actually kind of maybe work with your Kubernetes cluster. So when you want to look up a resource, you can kind of look to the files you're using to define those resources to know how to look them up. So like, for example, here I have service and deployment. Well, if I do kubectl get deployment or kubectl get services or get service, that gets me back those types of resources. So by looking to the file where you're defining a resource can tell you how to then look up that resource on Kubernetes by kubing kube get and that resource type. So we also look at the metadata fields, like for example, name. If we do kubectl get service and then the name of that service, and that will get that specific resource for it. So it didn't matter too much just because I'm using an extremely small Kubernetes cluster that has, a very few things on it. But if you're having a Kubernetes cluster where a few other people are working on it, so you're going to have a lot more stuff out there, this can be helpful for narrowing down the search criteria for things that you're trying to look up for. So it's also important to understand the relationship between the different Kubernetes objects. So we have a deployment, and they have control over the replica sets, and then they have control over pods. So if I do kubectl get deployment, I see the hello service deployment. If I was to do kubectl get my replica set, you see it starts off with hello service deployment, and then it has a random ID of some characters and some numbers. If I do pods, I get hello service deployment, and it has also, again, random characters as numbers. They can see how that it's 55 CB, just like the replica set. For the pods, it starts at 55 CB. So you can see how that replica set has control over these pods. So this can be kind of helpful if, like, maybe you thought you updated your Kubernetes deployment out there with like a new image name, and you go out there, you're not getting the response back you're expecting or the behavior you're expecting. You can kind of maybe start to look this up and be like, oh, wait, maybe it didn't get updated. Maybe there's something wrong with it because it's still kind of referring to like this older version of it, or like this new thing that's not getting updated. So kind of understanding those relationships could be helpful in the debugging process. There's also a concept called namespaces within Kubernetes, and this can provide a virtual breaking up of a Kubernetes cluster. So that way, if you have a bunch of people working within a Kubernetes cluster, but you don't want to have to get the additional physical hardware, you can just use namespaces to break them up. Just kind of like the same concept that would be namespaces for almost any time other in computer science. But if you want to get calling across all namespaces, you can just add the -A. In that case, I get all the pods across all the different namespaces for my Kubernetes cluster, which has default, IBM system, kube system, and then also a custom namespace I made it of test. If I wanted just to look for a specific namespace, I could just add the -N and then the namespace I want to look at, in this case, test. If I wanted to change the default namespace, of course, the default namespace by default is default. But if like we have multiple teams working within the same Kubernetes cluster, and we had those namespaces divided up by teams, instead of constantly maybe always having to put my -N and then the team name or the project name I was in, I can just do kubectl config, set context current, and then whatever the namespace I wanted to have to be my default namespace. And now when I do get pods, I'm only getting back the pods from the test namespace. So you can also view more detailed information about the pod or the resources. So if I do kubectl get nodes, I get back a few fields. But if I do nodes -O for output wide, I get back more information, like, for example, the external IP address to that node. Also, I can do kubectl get service, and then maybe the resource I'm going to look up. I can also do the output of YAML, and this would actually get back the actual declaration for how actually kubectl or Kubernetes, the Kubernetes controller, is actually trying to declare it. So when I actually apply like my deployment file out there, Kubernetes will kind of add some like annotations and additional information, like maybe when it was applied, when it was created, and stuff like that to it. So you can actually see the full declaration for how Kubernetes, that state it's actually trying to maintain for that Kubernetes resource. So you have both YAML and you can get JSON. It's going to return back identical information. Of course, just the format would be YAML or JSON. There's also kubectl describe, and then the resource you want to have described, which can also provide a lot of the same information back, just in a more command line or console friendly format. You can also inspect pods, which is going to be really important for debugging. For example, getting logging back. So you have like the pods you can get back, and then if you want to get the logging to that pod, you can do kubectl logs and then the name of that pod. But if you want to look across multiple pods, you can also look at pods that match based upon metadata information. So for example, this app, if I was to do kubectl logs -L, so that's label. So you have labels here and this here. So -L for label, and then the field within that label, in this case app, and then hello service, I would get back all the logs across all the different pods that match to that criteria. And you can see here in these concatenated logging statements that I'm getting back the logging statements for both of the pods, not just one of them. You can also run commands within a pod. So if you do kubectl exec, the name of that pod, and then --, you can just provide whatever kind of command based upon the operating system for that container. In this case, it's running a Nix-based operating system. So I just do an ls, and then I get back a list of all the different, the directory list at the root of that pod. But you can also do this thing for like doing thread dumps and other kind of diagnostic and debugging commands as needed. This is how you would do it with the kubectl exec command. Also, you can do a top on pods, and it works pretty similarly to how logging would work in that you can do it by individual pod, or of course also by using metadata labels to get multiple pods back. But then from this, you can get an idea of the resource usage of the different pods and containers you have running out on Kubernetes. Cluster info can be really useful. The basic cluster info just provides some generic information, diagnostic information, which isn't too helpful. But cluster info dump, that can be very helpful if you're having an issue with a container or a pod failing to start up, like you have crash backoff loop, error creating pull image, or something like that. Stuff you'll run into if you start using Kubernetes enough. This can be very helpful for trying to debug what's actually going on. So dump will just pull it back to your console. It can be an overwhelming amount of information. So I would generally recommend using an output directory, which based upon where your terminal is, this will output information to that directory based upon the different namespaces. But that can be very helpful to kind of look in and debug maybe what's going on when you're having an issue where a container or a pod isn't starting up and you're not getting any logging information back because it fails even before that point. Cluster info dump can be very helpful for figuring information out. You can, of course, also update resources. And again, this is where I'm talking about from a perspective of a local image or local cluster or a development cluster. You wouldn't want to do this. You wouldn't want to manually update images to the CLI on a production instance. You would actually want to have that all backed in version control for actually how that's declared. But for when running locally for debugging purposes, this can be helpful. So example, if I wanted to add more instances of a pod, I could do kubectl scale and then how many replicas of it I wanted to have. So I had 3, then I could get like another replica started up of it. You can also do kubectl edit, and then that could bring up whatever that terminal's via our editor is, like for example, VI. So here I can see that edit a deployment. It brings back the full thing of how Kubernetes has it declared out there. And in this case, I'm going to update the number of replicas from 4 to 5. And then I save it. It gets updated. And then now when I call back, now I have 5 replicas, another one just starting up based upon what I just changed. All right. So there's also some design considerations for Kubernetes. These aren't things that are entirely, a lot of these practices would be good even outside of Kubernetes. It's kind of like, think of it in a way of like continuous integration, continuous delivery, and microservices. Continuous integration and continuous delivery would still be relevant even if you're building and running in monoliths, but they become absolutely necessary when you're doing microservices because you're going to have so many different applications to push to production. You can't be doing it all manually. This is kind of the same thing with this. These are some of the things you kind of need to do if you're going to be running Kubernetes, just because if you don't have these, you're going to be kind of constantly running into issues. So you kind of want to make these changes, but they would still be relevant even outside of the Kubernetes context. So some of this, when you're containerizing it, you want to actually increase the number of layers within your Docker image. So if I was to go in and make a small change to this hello service, even though I'm only making 5 lines of changes here, when I rebuild it, I'm pushing out that entire Docker layer image because all my application code and dependencies are all in a single layer. So Spring Boot 2.3 added the ability to add layers to your Docker or to your Spring Boot image. And so here I'm extracting all those layers out from when I'm building it with Maven, and then copying in as separate layers where I have dependencies, snapshot dependencies, the Spring Boot loader, and then an application code itself. If you want to do a multi-stage Docker file, this is how you can work with it. Multi-stage Docker files can be helpful because if there's certain resources you only need at one stage of it, then you can have them removed from the actual final product you're building, which can make both the image smaller, which is obviously helpful, but particularly it also makes it less vulnerable because if there's some sort of exploit in some other previous step you just didn't know about, if code isn't there to be exploited, then it can't be exploited. So layers and multi-stage Docker files can be very helpful for that. Going on though, by splitting up these into multiple images or multiple layers, now my application code dependencies are located across multiple layers. And the way the layers work is that if a layer doesn't change, then it's not going to be rebuilt. And you want to have the layers that are going to be changed most often push layer. But imagine, I'm pushing this Docker image up there initially again, and then we go through the same change of like I'm adding that new resource endpoint to it. Again, only 5 lines of code being changed. Then when I repush this, instead of having to push the full 28 megabytes out there, I'm only pushing 23 kilobytes because I'm only changing the application code. All the dependencies and stuff aren't being changed, which are in lower layers. So you would want to generally increase the number of layers. And again, there's a lot of pre-built tools like in Spring Boot and other areas that can kind of provide a good basis for this. So you don't have to, it's not too difficult of a task. Individual layers are smaller. And then place layers that are going to be changing more often. For example, your application code should be the last layer within your Docker image being built, other than the layer they're going to be executing. Place those layer more often, or place those layer in the build, because when a layer changes, then any subsequent layer is also going to have to be rebuilt and repushed, because obviously, that's the way it would work. Also, multi-stage Docker builds are good. You can have a smaller final image by placing temporal tools in a separate state, and you would name those stages so you can be referenced in a layer state. So another thing is liveness probes and readiness probes. So it's important to understand liveness and readiness are not equivalent, and liveness and readiness aren't also necessarily equivalent to health itself. They're all related, but they all have specific purposes. So a liveness probe is this application in a normal state. A readiness probe is this application in a state to service request. So you can more think of it as liveness is going to be a terminal state. If a service is no longer in a live state, then it's probably going to have to be stopped and restarted. Readiness is going to be temporal. Application can just be a bit overwhelmed right now, so stop sending requests to it to give it a few seconds to restart. So to configure this within our deployment file, we could have a liveness probe and a readiness probe. In this case, we're doing HTTP GETs, but you can also do command line pings against it. But I'm telling it within the container, the endpoint to hit. So actuator, health, liveness, added in Spring Boot 2.3 were the native concepts of liveness and readiness, but you still need to add the actuator dependency to your application. But that's the endpoints to call. And then in this case, we're telling Kubernetes to wait 5 seconds after we tell a new pod to start, to wait before trying to call to make sure the application is either live or ready. Then we're also saying that wait 3 seconds between each call to check again. So call readiness, okay, 200. Okay, wait 3 more seconds to call again. And then finally, the failure thresholds, how many non-200 responses to get before either, in the case of liveness, to restart the pod, or in the case of readiness, to block traffic to that pod. So what does this look like? Let's actually kind of see an example of it in action. I just put together modified the code to where I can manually set these probes to whatever state I want it to be. So I can set liveness to where it's broken, readiness to where it's not ready. So at the top of it, we can see the status of my cluster, and the middle request to see how the cluster is being servicing those requests, and the bottom me hitting those endpoints to change the state of it. So right now we see my Kubernetes cluster servicing those requests. Now if I set readiness to false, you can see now, whereas there was one instance ready, now it's 0, and now requests are being blocked, but the instance goes back to being ready, and now it's servicing request again. Now, if I was to set the liveness here to false, run that in just a moment. So now the application is broken, and you'll see after a few moments, Kubernetes again calls it. It says, oh, wait, it's broken. And now it's trying to restart the application. Of course, I can't succeed in calling that application because it's currently being restarted. After a few moments, it completes restarting. I can call it again, and again, the requests are being serviced. So how should we use these probes? I would definitely recommend reading Release It by Michael Nygaard. And there's a newer version of it. This is the 1.1 version, or the version 1 of it. There's a version 2, which I probably would recommend reading. I haven't read it. This is the version I read. But the concepts I want to talk about is called cascading failures, bulkheads, and blocked threads. So if you were to tie liveness to some sort of downstream service like a database, here's what would happen if you did that. For some reason, that database goes down. Who knows? It could be being configured, someone just brought it down, or it could be getting overloaded. Whatever the reason, though, you bring it, it goes down. Now all these other services are going to go down with it, and Kubernetes is going to be trying to restart these services constantly. And that's going to continue to overload that database, because as these services are restarted and come up, they're going to try to connect to that database to set up their connection pools or whatever it is, and that can continue to be in an overloaded state. So this is a cascading failure. Our database fails, and now other upstream services are failing, so a cascading failure. So instead, what you will want to do is actually tie readiness to downstream services. Same scenario. The database goes down, for whatever reason, but instead of having these services go down, they'll just stop servicing requests. And then this would give that database time to recover, because it's no longer having load put against it, so it can much more easily recover if it was overloaded, or if it was just being restarted or whatever like that. Well, it's just going to be a little bit easier to kind of restart without kind of having to immediately set up connections, because upstream services are calling it. And of course, also you're not wasting a bunch of resources by constantly having to restart these services on your Kubernetes cluster. So this is called a bulkhead. Just kind of like in a ship, a bulkhead will come down because one of the compartments is getting flooded, and you don't want the other compartments to get flooded. So this is what a bulkhead stops service requests if that downstream service goes down. Of course, you still need liveness. So whatever reason, in your Hello service or one of your services, you have a data, like you have a memory leak, or threads are getting used up, and eventually it may get completely used up to where it can no longer service this request, and eventually you maybe have a bunch of zombie services, at which point it's good to have the liveness probe there, so Kubernetes can detect maybe this service needs to be restarted for whatever reason, and it can be able to do that. And this kind of goes to the concept of quote-unquote blocked threads. This is a bit of a broader concept than specifically focusing on threads within Java, but just to maybe an overall blocked or consumed process or dead process. That's where you would still want liveness in it. But you also have graceful shutdowns. So, Kubernetes may just be killing services or restarting services based upon, these pros we have, or because you're updating versions or whatever it might be. But it would be important, though, that you maybe give these services time to stop, because they might still be processing transaction. A user might have just placed an order right at the time that kill command was set, or, like a fifth of a second before a kill command was set. And you want to give that container some time to finish up that transaction before you're killing it, but you want to block traffic to it because you don't want to have other requests coming in, because otherwise you're going to be in that perpetual state potentially. So here we have this long running process, and just going to start a process that takes 5 seconds to complete, and but it gives back an immediate response. Kind of same thing, the overall status of the pods, just setting them down. And you can see here in the center, processes are being started, processes are being completed. If I was to scale down the number of replicas, though, as I'll do here in a couple of seconds in this example, scale down the number of processes to 0. And now we see processes aren't completing because Kubernetes is immediately setting down a container when that SIG terminal, the kill signal, is sent. So you can, by default, it's a 30-second termination period, but you can define a termination grace period within your deployment before killing a pod. And then you can define, like, for example, here we can say lifecycle pre-stop and then send like a sleep command before the termination signal is sent. There's a number of different ways you may configure it. So this is one example. Another example, added as part of Spring Boot 2.3, you have a server shutdown graceful, and you have a Spring lifecycle timeout, and you can say like how many seconds Spring Beans have to shut down. In my case, for this tax executor that I'm running to kind of simulate these long running processes, I also had to specifically configure it to say, hey, at least give it 10 seconds to kind of finish up before shutting down if there are threads running. So now I make these updates, and I kind of again kick off some processes to get them started. Now I send a kill to stop it. So you can see processes are still being completed, but at the bottom, I'm sending more requests to it, but they're being blocked. So that's exactly what Graceful Shutdown is. Give this pod a few seconds to finish up whatever transactions it might have, but don't allow any more traffic into it, which can be, again, very important to make sure you don't accidentally kill some processes in the middle of state or middle processing, and now you have like a weird unknown state. All right, the last section we're getting to, and I think we have enough time to get through it all, is coming with persistence and configurations for applications within Kubernetes. So the first one we're going to look at is a volume. So if you write anything to inside a container, when that container goes down, all that information is gone, but there might be cases where you want to have information persisted. Of course, like databases would be an excellent example of that. Maybe you want to have your databases running in containers as well, but of course you want to have a volume where that data is actually being written to, because you don't want to have all the volume go down when your database goes down. That would not be good. So volumes provide persistent storage outside of a pod container. And of course, this could also be good for like caching. So here's another example for just setting up like a simple H2 database and knitting information just to make sure like it's actually being persisted. And I'm saying like, hey, references to like the volume mount location within my database, and then to also just update it. So if there's existing data there, don't get rid of it. So here, without using any sort of volumes, you can see at the bottom here, when I call for data, there's no data there. I initialize the data. I call data again, and I get back the data that I have added by default. So if I restart it, it's going to take a few seconds, and I want to get through this, but the bottom line is when I call this data again, it's going to be gone because I was persisting it inside the container. And when, again, the container goes down, it's going to be gone when I try to get it back. Just trust me, it actually works. The data is actually gone. So now I can just add a volume mount and add that to the volume mount path, like I referenced in my data source controller for where I want to have H2 store data on my file system. And in this case, I'm using host path. And if it's not there, create this directory and all this. You would not only use host path for storing any vital information. It could be okay for caching, but host path is tied to the node that a cluster is running on. And if that node goes away, which could happen again at real scale, all that data would go away with it. So don't use host path for anything of real importance when it comes to really persisting data, though it can be good for maybe for caching or something like that. But like I said, the volume mount, that's where I'm mounting that directory onto. And now if I run it again, if I was to restart this container, it would actually return the data to it instead of actually being deleted because that container has been deleted We're running close on time, so I'm just going to kind of skip through this example, but trust me, it works. I can send you the slide deck. You can actually kind of see it for yourself that at least this example works. Volumes, there's going to be many different options, and it's going to vary depending on the cloud provider and the storage choice depending on the need for that application. So I can't really give recommendations. It's going to vary so much based upon need and the cloud provider that you have. So also, you're going to need to provide configuration information. In dev, you're going to be connected to a certain database. In prod, you're going to be connected to a different database. And that goes for a lot of other services and stuff you're connecting out to. So you need to be able to provide this configuration information based upon the environment that you're in. And there's many ways of doing that within Kubernetes. There's environment variables, and this passes in configuration info at the startup of a container. And within my deployment file, I can just define an env and then the name of the environment of the environment variable and whatever value. And so here, environment message. So that provides that association. And then here, this is like a simple control I have just to demonstrate this out. When I get config for an environment, I'm getting back the message or the value of that environment variable I passed into it. ConfigMap, you can actually just add that as like a different resource within the cluster. And it's just good for when you want to externalize a more complex configuration information than what you would have with an environment variable. In this case, like I'm putting the full application properties within this config map. And then I add it to my cluster definition. And then I mount it just kind of like I would a volume like I did just the previous example. Here I'm using Spring Config. And you can see the Spring Config name as what I find it into the config map. And then the application property for the volume mount. And then I'm mounting it onto like the application config, which is a place that Spring will look at to pull in configuration information. And then here again, I'm pulling back reading properties from the config map just to prove that, again, it works. Secrets, when you're connecting to the database, of course, you need a username and password. Or maybe for SSL certificates or any number of things, you're going to just need to have certain things to be encrypted because they're sensitive. That's what secrets are for. You have to encode those values as base64 values. I create the secret with the base64 values. I apply the secret just like I did a config map to my Kubernetes cluster. And then I can just, again, reference it, database connected info here. And then that's how I reference the database connected info, pass it in as arguments to my container, and then I'm able to connect to the database and then also pull up my super secret message that I added to my secret just a few steps ago. Whew. I know I went through that really quick. Hopefully everyone caught everything and enjoyed this. If you have any questions, now would be a good time to ask. The code that I showed in my examples here, you can view it here, Java on Cube 101. If you have any more questions you didn't get a chance to ask him here, you can hit me up on Twitter at Billy Korando, or you can send me an email, william.korando@ibm. I'm not just saying that. I definitely like to interact and talk with people. I got into developer advocacy because I want to help people be better developers. So definitely reach out. I'll be more than happy to answer questions. And don't feel like if it's a question like seems too dumb, don't feel that, because I know I've definitely had a lot of dumb questions myself in my time, and luckily some people were nice enough to answer them even when they seemed like that. So have a couple minutes still. I said I'll be here for any questions you might have. But otherwise,
okay,
hey, Jose.
Okay, guys, if you have question, please, this is the time. We have 40 persons connected right now.
Oh, great. Yeah, glad to see a good number of people showed up.
Okay. Some question, guys.
Yeah.
Please, only leave your question in the text box in YouTube or Facebook chat. It's very simple. Okay. The people
it
is
happens
shy.
sometimes. Yeah. Not a problem.
Okay, Billy, thank you very much.
Thank you.
We
Thank
have no
you,
more
Jose.
questions. Thank you. Have a good day and see you soon.
Yeah,
If
see
you
you soon.
want
I'll
to
see
give
you one
some
tomorrow.
final words or say goodbye. Yeah, exactly. See you tomorrow. You
how
have
would the physical
final words? One question.
I'm not quite sure what you mean by how the physical model would look. Like, what would like all these concepts like to look like out in the cluster? I'm not sure. Sorry.
Yes. Please, Paul, more details.
Yep. So yeah, sorry, I'm not quite sure what you mean there. Otherwise, Paul, send me a text, like on DM or an email, and maybe we can figure out an answer to your question. So otherwise, I think I'm at time. So I'll make sure to keep everything on schedule, and I guess sign off here.
Okay, Billy. Thank you. See you
All right,
tomorrow.
thank you. All right, see ya.
Take care.
Bye.
Bye-bye.